We're now ready to begin our exploration of how matter itself can behave as waves. And we're going to do this by starting with the classical wave equation and showing how it forms a basis for understanding how we might relate matter as a wave. Now, I've written up here the classical wave equation once again, as we have drawn it before, and I also wanted to remind you of some other relationships that, for example, the wavelength and the frequency of light, when they multiply together, they get the speed of light. This is generally true of traveling waves, that when we multiply the wavelength times the frequency, we're going to get the velocity of the wave. So in this case, c is the velocity of light, but we're actually going to use this version a little bit more in this case. I also wanted to touch base with the definition of an angular velocity, omega, or an angular frequency, and it's related to the frequency that we're used to over here by a factor of 2 pi, and we're going to use that as well. All right, so how would we go about taking the classical wave equation and expressing it in a way that makes sense for matter? Well, one way we might do this is to write our solution, to separate it into a coordinate part and a time part. And we know that this separation of variables works with this as long as the velocity of the wave is constant. And I'm furthermore going to quote, if you will, the general result that we got before, that we could write this time-dependent part as equal to the sum of trigonometric functions. Okay, so we're assuming that we've got a ordinary differential equation that has a negative component. So it has something like this. And indeed, if we plug this version of t into this equation, this would be the result. Okay, so this is the angular frequency of the wave as it moves in time. All right, so now if I plug this version of the solution into the classical wave equation, what would I get? All right, well, I have a second derivative with respect to x, so we know the second derivative with respect to x of a product of two functions, one of which depends on x and the other depends on t, is just going to give us this. All right, on the other side of the equation will only affect the t part, and so the other side of the equation will look something like this. We'll have d squared u of dt squared would simply be the coordinate dependent part times the second derivative with respect to time. But we've already seen that the second derivative with respect to time is simply going to be omega squared. So I can simply write this way. All right, so now if I put these together into the framework of the classical wave equation, I'll get an equation that begins to take shape for our coordinate dependent part, and that's the part that we're going to be most interested in. So I'll have minus omega squared over v squared. The minus sign is coming from over here. And you'll notice that both sides of the equation have the function t of t present. There's only psi of x on the right-hand side because we have a second derivative of it on the left-hand side. But we can divide through by this t of t, and so I'm going to just cross them out here. And that will leave us with an equation that really now is an ordinary differential equation. So I'll change the partial derivatives to real derivatives, and we'll have something that looks like this. Okay, well that's great, and this is actually, in some ways, this is leading us toward what we're going to need to find that, the result that we know as the Schrodinger equation, but we need to somehow translate this stuff here into something that's meaningful for molecules. Well, I guess one way to go about doing this is that we're going to take this set of relationships that the angular frequency is related to the regular frequency this way, and the regular frequency is related to the wavelength via this. So if I change that around and say that I have the angular frequency or the frequency is v over the wavelength, then I'll have 2 pi v over the wavelength here. All right, now this is where we want to bring matter in. And in order to do that, we're going to take the de Broglie hypothesis that basically said that the wavelength of matter was equal to the Planck's constant divided by its momentum. But I want to switch this around and basically rewrite this so that we're solving for the momentum is h over lambda. This is the same as we saw earlier for light. Okay, so when I have this, then this really means that 1 over lambda is equal to p divided by the Planck's constant. So I can substitute that in up here to make this be 2 pi p over Planck's constant. All right, we're beginning to get closer to something that's going to be useful for us. I want to make one more change, and that is a fundamental definition that we often use in discussing wave mechanics of small particles, and that is to say we're going to define a new constant, which I'll call h bar, which is simply Planck's constant divided by 2 pi. Right? It turns out that this comes up a lot, and we can see that that is apparently present here. So in the end, we're going to get something that says that our angular frequency, omega, is simply equal to p divided by h bar. All right, so now we have, and I've somehow neglected to include that factor of v in all of this, so that's still there as well. So now we have everything we need to translate back in here. So when I rewrite this, it's going to be p squared v squared over v squared h bar squared. And now I can convert this to p squared over h bar squared. And of course these are still multiplying the function psi of x. All right, finally I want to invoke our classical expressions for energy. We can write the classical energy of a particle as equal to its kinetic energy plus energy due to some potential. But this kinetic energy can also be rewritten as m squared v squared over m plus v of x. But this m squared v squared is just p squared. So this is just p squared over 2m plus v of x. Okay, now I can take this equation, E is equal to p squared over 2m plus v of x, and solve for p. And if I do, solve for p squared. So if I do that, I would find that p squared is equal to 2m times the quantity E minus v of x. Well, now I can take this and plug it right in there. And what I'm going to get now is a very suggestive result. D squared psi dx squared is equal to minus 1 over h bar squared times this stuff, 2m e minus v of x times psi of x. All right, so let's review what we've done up to this point. We've taken the classical wave equation. We've solved directly for the time-dependent part in terms of an angular frequency, omega, and we've then plugged this into the classical wave equation, plugged in a product solution to find an equation that is an ordinary differential equation just for the coordinate, spatial coordinate part. All right, we've then massaged, if you will, the angular frequency to express it in terms of the regular frequency, then the velocity, then the wavelength, and then we've used the fact that de Broglie's hypothesis relates the wavelength to the momentum, and if this is, this is true for both light and for matter. And having done that, we now can take the classical equation for the total energy and relate the momentum to things that are energy-related quantities. All right, so that leaves us with this equation here. Now, if I rearrange this equation, okay, let's say I multiply both sides by h bar squared over 2m, I'll have negative h bar squared over 2m d squared dx squared is equal to e psi of x minus v of x psi of x. And if I move this part over to the other side, I will end up with the equation negative h squared over 2m times the second derivative of psi with respect to x squared plus v of x times psi of x is equal to e psi of x. And this result is the one that we've been going for. This is the Schrodinger equation. And as I said, this is not a derivation of the Schrodinger equation. It is simply an argument that supports why it has the form that it does, and perhaps uses some of the reasoning that Schrödinger might have used in coming up with the equation. But the equation itself is not based on known information that we have then used to derive this equation. It is simply taking the classical wave equation, applying it to matter using de Broglie's hypothesis, again an unproven hypothesis, and using that to come up with a formulation for how we might deal with matter on a wave-like basis. Well, it turns out that this is the fundamental equation that we'll be using throughout the course. So this is a very important equation for us, and we'll have a lot more to say about it in things to come.